Okay, before the day is finished, we need to get going here. So I'm going to introduce Scott Tilley. He'll tell you what he's doing, and maybe you can start off a little bit about yourself. But you're not an astrophysicist or anything like that. Not yet. Not yet. Okay. So like an amateur astrophysicist. But I'll let Scott take it over and make his presentation, and then you probably have lots of questions and stuff after, but you'll be able to corral Scott when it's over. Okay? Stand by. Next voice you hear will be Scott.
Thank you, Dave. I'm Scott Tilley, B7TIL. I track satellites by radio and optical means. I am an active amateur radio operator. You might not hear me too much on the air these days because I spend most of my radio time satellites. But I have been quite active in the past. Those in the North Shore Amateur Radio Club know me as an LFDXer. I worked with RAC and a couple other experimenters in the 2000s, getting the 2200 meter band sorted out as an experimental project, and completed that project once the band was given to the amateur community in Canada by completing the first QSO in Japan on 2200 meters. So after that kind of mainstream, I needed to, that's the way my mind works, move on to another experimental project. So I looked to satellite tracking. As a youngster, I took quite an interest in amateur radio satellites, Oscar 10, Oscar 13, Oscar 7, we all know them. And played around with them, built antennas, spent a lot of time in the machine shop in high school doing all kinds of neat stuff with amateur radio. And as everything else starts to happen in life, family, job, all that kind of stuff kind of catches up to you. So satellite tracking kind of went into the back burner. A lot of stuff happened over the years, and satellite tracking suddenly took a little bit more of an interest in it. Not so much technically, well, there's a lot of technical as we'll see, but also geopolitically, and just the transparency in our lives. So let's begin the presentation, and here this is not about just the recovery of image. I know the presentation title is Lost NASA Satellite. We'll talk about it, but I want to tell you about the journey, about why people watch for satellites, and why you might consider it an interesting aspect of the hobby. The dawn of the space age. We all know the story. Press the wrong button. There's an audio clip here. Yeah, that's exactly right. Okay, we'll let that beep on. So, with that signal, amateur operators around the world verify the reality that the Soviet Union had launched a satellite into orbit. We were the community that really released that information to the world, and the world believed it. Not too long after the launch, the first optical video of the first stage booster occurred. This is the first evidence of a satellite in orbit recorded on video. It was subsequently recorded on 16mm film. This footage was actually used by one of my colleagues to reduce the orbit of the booster and produce the first really accurate orbital elements, believe it or not, of the Sputnik 1 rocket booster. You might be thinking, hey, wait a minute. Sputnik 1 was the first thing over. No, it wasn't. The booster was. It released the Sputnik satellite into orbit, and the two that remained in orbit for some time, and then behaved. So what was going on at the time? We had all the governments in the world keeping an eye on space? No. We had a group of amateurs that had been preparing for the space age. It was a group of people like us sitting in this room that were out training with binoculars and small telescopes and getting ready to to observe the first satellites, because 1957 was the geophysical year. It was an effort around the world to start collecting geophysical data about the Earth and the Earth's space environment. Sputnik presented the first opportunity for these guys that have been preparing to observe satellites in orbit, to learn about our upper atmosphere, to learn about the Earth-Sun connection by actually establishing orbital elements for the satellites and seeing how they behave, how the radio signals reflected through the ionosphere of space. How did that work? These guys were from a project called Operation Moonwatch, and for the first few years of the space age, they were the primary source of satellite trajectories and information until the US Air Force and other militaries around the world started getting their act together. Amateurs really got involved in radio tracking, particularly as the manned spaceflight programs got going in the 1960s. Here's Greg Roberts, or one of Greg Roberts' colleagues. Greg Roberts is a legendary amateur radio operator in South Africa. I can't remember his call, but he has been involved. He's a professional astronomer. He's now retired, and he's been involved in satellite tracking since it began in the 1950s. He was a member of Project Moonwatch, and there was a really big community of guys in South Africa. He's in a retirement home now, and out the window of his retirement home is a telescope set up that auto-tracks satellites and collects data and reports it daily. He's one of those kind of guys that just inspires you. And he'll answer questions. He runs a big Facebook group and answers questions and mentors a lot of younger observers. So, satellite tracking by the mid-60s, visual tracking started to fade away. It was less important. Big governments started taking it over. The big governments were reporting everything. Everything that went in orbit, everybody pretty much knew what was going on. So everything looked good. Amateurs then turned their attention to other interesting things. Automatic picture transmission from satellites, weather satellites and whatnot. It's one of the first stations. This is Greg Roberts' station in South Africa. Notice the reel-to-reel tape recorder, the receiver, and then the oscilloscope used for the images. So that's a pretty determined guy. And look at the array he's built here. We'd love to have that on JT65 off the moon. I would. So I've got a 7-element array myself for EV, and this was 1960s. As the Apollo program came around, S-band became the primary downlink for the civilian and military space program. There's 100 megahertz of spectrum between 2200 megahertz and 2300 megahertz that's dedicated to space and Earth communication. Amateurs built dishes, aimed them at the moon, and listened to the Apollo missions going around the moon, on the way to the moon, and on the moon, and actually heard audio and established the credibility for deniers that there was something that was going on there. So why do we do this? Why do we look up? It seems kind of passé. The US Air Force is telling us everything what's going on up there, right? Transparency in the use of outer space. So it really began in 1967 with the Outer Space Treaty. So most of the spacefaring nations, if not all of them, in 1967 agreed that space should be used peacefully. It should be a non-military place, really. Definitely no weapons of mass destruction. We can't put nukes in orbit and deploy them at your will. And nation states can't go around in space claiming sovereignty. They can't land on the moon, put up their flag, and say it's now American territory, or vice versa, Russian territory, or Japanese territory, or you show up and decide to create your own sovereignty and say, it's my territory. You can't do that. Space is space. It's there for us to use and enjoy, but we can't own it. 1976 comes along. This is a significant change or addition to the Outer Space Treaty. They created the Registration Convention, and we'll see in a few minutes why this is so important. Signatories agreed they shall report what they put into space to ensure transparency. So, no secret space missions. You have to tell the rest of the world what that rocket put up there. What's it used for? Is it a weather satellite? Is it a military satellite? Is it a communication satellite? Give us some basic orbital information. It's kind of like air traffic control. Tell us what you put there and the basic trajectory that it's in. What's the purpose of the object? like I said earlier, is it for communications? Is it a military payload? It's not a bad thing. It's a military payload. You're allowed to do it, but tell us what it is. Who controls it? Who owns it? The idea behind the registration convention was to ratchet down the kind of the geopolitical environment around what we're putting in space. Because when you look up and you see a satellite, you only see a dot. You don't know whether it's a nuclear bomb waiting to be deployed, or whether it's there to take pictures of the weather and make sure that we have accurate weather forecasts. You don't know. So what happened is the Cold War went on, technology advanced, and in 1984, the Reagan administration, who was on the they had a Star Wars thing going, and they had a bunch of other military projects that were underway. They decided to start classifying orbital elements for military payloads. What that meant is the U.S. Air Force would release on a regular basis. Back in those days, it was a big print out. If you were on the list, you got this package in the mail of all the orbital elements of satellites in orbit. So the U.S. Air Force decided to redact anything that had a military purpose, or whatever they thought. And even at the time, the infant GPS system was redacted because it was a military, which was kind of redundant because the satellite tells you where it is. It sends down the orbital elements. They've since corrected that. But they stopped publicly reporting on their own military missions and that of their allies. Their registrations became very, let's say, generic. If you look at the UN registry for satellites, the United States basically says it's a satellite. It might be carrying on communications, it might be doing weather observations, it might be doing science, or some other purpose. And that's what they say for every launch. Meanwhile, countries like Russia, China, European Union, and most of the other spacefaring nations, they're pretty fastidious. Some of them are, but ironically, the Russians are the most fastidious. Even when they're in the Soviet Union, they're very, very precise about what they put up there, and they give real trajectories. If it's a military mission, they basically state that the satellite is launched by the Ministry of Defense, and it's being used for that purpose. They don't tell you that it's what exactly its military mission is, but they at least tell you it's a military payload. The big thing to note is amateurs took interest. The game's on again. So we've gone from the early 1960s and the late 1950s when amateurs were providing critical information about what was in orbit, helping keep track of things. As the military's caught up, amateurs were used to help deal with finding satellites that have problems and issues after launch. Then eventually the military said, we got it. We really don't need the amateur community anymore. And we started defund the support of the amateur observers around the world and started to wrap it up. Project Moonwatch by the end of the 1960s evaporated. And a small core group of people continued to track. By 1984, the US government gave those people and a new group of people a reason to track. By the late 1980s, early 1990s, the U.S. launched the first MISTY satellite, USA-53. USA-53 is something completely different than ever been launched in orbit before. It was a stealth satellite. It was designed not to be seen or heard. So they launched this thing from the space shuttle, I believe it was STS-36 in 1990, and it was deployed into low Earth orbit. It was initially tracked with a bunch of debris and vanished. So its mission was seen. What happened a few months later, he let the sun reappear. But nobody in Europe ever really saw it. People in North America saw it on a regular basis and kept tracking it for a while. And then we think the NRO, the National Reconnaissance Office, kind of clued in. Oops, we forgot. There's amateurs watching us, not just nation states. Amateurs were recording the position of this thing. What we think they were doing was either to save fuel or some other resource on the satellite. They were deactivating the cloaking device essentially over friendly places of the Earth, and only activating it when they were flying over the Soviet Union. So they realized that was not a good thing to do because people are going to observe it and report it, and it gets added to the catalog the amateurs maintain. So as the MISTI program developed, USA 144 was launched. So in 1999. The administration or the NRO said, okay, they got us the last time, they're not going to get us this time. So they launched this thing, and there was this big dog and pony show in orbit. All kinds of weird stuff happened. They launched it on a weird trajectory out of Cape Canaveral, went into orbit. There was puffs of smoke, and debris, and this and that, strange orbits that nothing's ever been sent into. And finally, the Russian government comes out and says it exploded. There's debris everywhere out there. And USA 144 disappeared. And what remained was, in a very odd 3,000 kilometer circular orbit, was a rather bright and odd satellite that has become known as the USA 144 decoy. And after years of observations, we've determined that because of its mass to weight ratio, we can see by solar wind perturbations and studying the object for years and its orbital behavior, the mass to weight is extremely low. So we believe it was an inflated mylar balloon that just dazzled and attracted attention. The actual payload of USA 144, nobody ever saw. It was lost to amateurs and was never been cataloged. These launches, if you go look them up in the UN registry, they don't say much. Then a Prowler was found in orbit in the late 1990s. What is a Prowler known as? It was the first satellite inspector that was launched into geostationary orbit. This one was an entirely black project. It's still not acknowledged by the US military. It was launched on STS 39 in 1990, and it was launched with another military payload. And a bunch of anomalies were noted at the time because they could launch two satellites into orbit out of a shuttle, and one of the booster rockets you'd see with one of the payload bay and spin around and send all these little videos back to Earth. A bunch of amateurs noticed, hey, wait a minute, it's missing a part for launching, for doing like two targets in the same orbit. You know, it's missing an adapter. Everybody's like, that's odd. And then didn't think much of it. Then two guys in Texas in 1998, Mike McCants, who maintains the amateur classified orbital element catalog, and another guy named Ed Cannon saw flashing stuff as they were scanning the geobelt. And they came across a satellite that they couldn't identify. It was in a geostationary light orbit, sitting out over the West Pacific, just off the coast of California, essentially. Ironically, in a position that the Soviet Union couldn't see. After a whole bunch of studying of the orbit of this object and optical analysis of it over the next couple of years, in the late 2000s, a guy named Tim Bolzapin wrote a report and was able to provide evidence of the orbital characteristics of this satellite and establish that it came from that shuttle launch. And using data from the European Space Agency about debris in geostationary orbit, was able to develop a very convincing case that this, in fact, was Prowler. Prowler was used, and we'll see here later in the presentation, we'll see modern-day Prowlers that aren't so classified, but are still classified, that do the same mission. Prowler was used to go into geostationary orbit and literally park beside an active geostationary communication satellite or other payload, listen to it, photograph it, basically spy on it, and then move along to the next part without the other guy knowing what they're doing. So it has stealth capabilities of playing near, and this was experimented with in the 1970s by the Lincoln Experimental Satellite 8 and 9, which were experimental military payloads, where they would take a plane near and then just angle the satellite in such a way that what you would see is not the sun being reflected back to you, but space. So the satellite, in fact, is stealthy. When they deactivated the satellite, they put it into a disposal orbit to have it ligate over Western North America. So effectively putting it out of reach of an active Soviet space surveillance program. So they wouldn't see it. Not, hey, what's this weird object that just appeared? Oh, wait a minute, they've been spying on us for the last 10 years. So they placed it in an orbit where it would be very unlikely that it would ever be seen by the Soviet Union. So Prowler was never acknowledged by the United States, and like the MISTI program, it created a lot of buzz in the amateur community about studying it. I observe this satellite every time I look to do a belt scan. You can pick it out. It just sits there live. It's long dead. You can see it flashing as it's tumbling in space. So just to give you an idea of what's really going on, this is kind of the secret space program, stuff you really don't hear about. So how do we find these things? How do we observe it? What are we doing? So we use very simple techniques, and we also use the state of the art. A combination of the two makes for very effective observing. Space has become a very, very busy space. There are thousands of objects in our orbit. This is a NASA graphic just showing you see the geostationary belt. You can see all this other stuff that's spiraling around. And you can see all the lower orbit stuff around the Earth. So there's this fuzz, this forest through the trees, if you will, debris, active payloads, and other things in space. So it's somewhat difficult to find a needle in a haystack there. But computers have allowed us to do this. It wasn't until the late 2000s that a very effective, complete, or very close to complete amateur catalog of non-reported objects in space was established and has been maintained since. And that's largely due to a small group of amateurs that submit daily observations of what they see. So what do we do? How do we track? Optical can be something as simple as a set of binoculars and a stopwatch. A lot of observers still use this technique. It's highly accurate for a trained observer. It's kind of like the CW of satellite traffic. The old timers still use this technique. There's guys in England. There's a guy up in Scotland. His reports every night. He's got dozens of satellites. He's in his 80s. He's out there with a set of binoculars and a stopwatch, and he just memorizes everything. He's just a robot at it. He just knows what he's doing, how he does it. I go out with a set of binoculars and my stopwatch, and I have to have WWD playing in the background, an audio recorder, because I can't remember all the details. So it just goes to say, when certain skill sets and training really be useful. I use more video techniques and a computer to do most of my visual observing. Here you can see what is called a 4-frame technique. So you take a 10 seconds of video, you sum those images up, then you get an average standard deviation, the brightest pixel of each image, and from there you can overlap known data. The black line there is known data from the U.S. Air Force catalog, and that blue line is known track for a classified satellite in our catalog, and you can see that there's 2 satellites passing through the field. So the software actually displays that once you've done the reduction and calibration. So it becomes pretty quick to find things that don't have a line. Those become the unknowns. Those are what you're looking for every day. And we find them regularly. So basic schematic of the system layout. For deep space, I use a Canon digital SLR with an 85mm lens and an f1.4 speed. And for low Earth orbit, I use a low light security camera, essentially, with a 50mm lens. It's fairly fast. It's in a weatherproof enclosure, and it's always on the roof on the same map on the tennis. I won't dwell on this. I'll be happy to share this presentation with anybody who wants, so we can study this a little bit more. This is the software package that we've created. Yes, we've been busy writing lots of software and frameworks to do all this. And it allows us to take the video, reduce it, convert it to satellite orbits, and then report the information to work. There's a bunch of utilities that we've created as well that allow us to see some of the results of those later in the presentation. So radio tracking, a little bit more interest to you guys. We all know what this is all about. Hands-on, turn the knob, listen to the VX. Well, when you're listening to satellites, it's not exactly that interesting. Most of the time it's just a solid carrier. Oops. So what we're looking for, or what I'm looking for normally, is this Doppler curve. I could care less if I hear the satellite or, I heard it. What I want is the data. And I want complete Doppler curves or portions thereof, so I can analyze that. Every Doppler curve for a satellite's pass is unique for the satellite's orbit and their position on the Earth. So you can take that information and reverse engineer it. When I started in the hobby, I was stuck in a world where Doppler analysis was very primitive. The only thing we had was the time of closest approach. Basically, the greatest frequency velocity or the greatest rate of change in frequency, that would be the time of closest approach. And if you would take multiple passes, you could make a guess at what satellite might be. Very clumsy and difficult panels. And as you'll see, that we've developed some software that actually converts that curve to velocities that we can relate to orbital elements and determine whether it's a known satellite or it's an unknown. So how do I collect that data? Well, I have a little 2-foot dish. This is for deep space stuff. I've got a search antenna, 16-turn helix, and I've got a small omnidirectional helix that points straight up. So the idea is, you hear something, you can locate it in the sky, you can pinpoint it in the sky. And once the dish is on it, it's now in the field of view of the camera, and it's dark, on goes the cameras, and you're going to get optical data as well. Once you have optical, you are in a state with the Doppler data to view only the target. You can tell what orbit it's in. And the more passes you get, the more you find your orbital gas gas. What does the S-band system look like? Presently, I omitted the long helix because I really find I don't need it anymore. Presently using the dish. This is for deep space stuff and around the moon. And out in the Earth L1 and L2 points between the sun. S-band is used out that far on missions, so I pretty much copied all of the space probe going around those points. S-band isn't used in the deep space. That's when we switch over to S-band. So then I have the omnidirectional multi-turn helix, and off it goes into an SDR. It's GPS disciplined, and I also have a monitoring receiver that allows me to put the cans on and actually look at something and listen to it. Which is often helpful when you're searching, or they just launch something and you have no idea what's really going on, and it's really kind of dynamic. It's nice to see the signal in real time and just disappearing into a FIFO and going to the hard drive and realizing how to do it. So here's the basic flowchart of how the software works. So basically the SDR dumps a whole bunch of data into a FIFO. There's a piece of software that does a fast forward transform, saves a binary file. Then we load it up into a piece of software that displays the spectrum in front of me. Then you insert brain power to decide what data you want to extract from it, and then out it goes in various files that we can now analyze and convert to orbits. So here's the story of how optical and radio tracking relate. We talked about Prowler early. This is what the U.S. Air Force now publicly acknowledges is our satellite inspectors and geostationary orbit. The rationale behind these missions now is geostationary space is very competitive. It's our communication system. Pretty much everything we take for granted in life relies on communication satellites and geostationary orbit. So the U.S. Air Force, part of the mission is to make sure they know what's going on up there. So the way they make sure they know what's going on up there is they send inspectors out that stealthily look around the geostationary terrain and keep an eye on what's going on. So how do they get them there? They put it on a big rocket and they launch it out of the Cape. And I happened to be watching as it passed over the rows in the west here out of Vancouver and captured this image. Meanwhile, the dish was listening for the upper stage boosters telemetry beacon. You know those nice little videos they send back. Well, on the classified mission, you didn't see the videos, but it's still there. They're watching it for their own reasons. So here's the S-band video download. And you notice the Doppler. Bingo. Bingo. I've got position, I've got Doppler, I have an orbit. So I was able to derive the orbit very accurately where it would reach insertion in the geostationary orbit. This this green line is the celestial equator, and where they park geostationary satellites. And the little red dot right there is the deployment of the satellite. That means I actually took a positional observation of that happened. The next night, I recorded this. This is the first stage, or the last stage booster, and started to refine the orbit over a number of months. This is the Doppler curve of it rising over my house and heading towards geostationary orbit. And with these, I was able to develop a very accurate orbit that allow me to record this. What we're going to see here, it's hard to see it right now, but there's a little dot somewhere in here right there. Boom. It started, it's empty. And now there's a stationary dot, a geostationary dot. First deployment, second deployment, contamination, avoidance maneuver, so, and then some else. So that's what an amateur can do. And you can imagine how the U.S. Air Force must have felt. There's a classified mission up on YouTube. Meanwhile, one of their contractors was doing the same thing, and I noticed on their Twitter feed they posted the same deployment. And so you get kind of a sense of what you can do with the right techniques, the right software. And you might be wondering, everybody in this room, how does this relate to amateur radio? We'll get to that. There's a couple of really neat ways that this relates to amateur radio, as I've discovered. A couple nights later, I found the payloads. They're very small. These little guys are supposed to be sneaky. I called them 99-119 and 99-120, because that's my unidentified sequence. As I catalog and identify, as I give them my own unique serial number. It's hers. So this is my deep space camera, and what you'll see next is a quick little drift animation. And you can see the thing come out of the noise and disappear back into the noise. So the orientation of the spacecraft and the position of the sun, this is changing every 10 minutes. These images are taken 10 minutes apart from each other. I was able to catch it just at the right sun angle and get it glint. Imagine you're looking at a boat windshield across the lake or something like that. The sun glints on it. It's exactly what we're looking for here. Just that coincidental, and you can see both of them doing it. So with that, we started to establish a position, and we were added to the catalog position. So everybody's in the room's probably heard of Zuma. So you take a billionaire that's got lots of really, really rockets, and you take a geopolitical situation that, where there's a country that's launching nuclear missiles and doing all kinds of crazy things, and you take a lot of anxiety, and then you throw in the next super secret military space mission. And you give it a very nebulous name like Zuma, and of course everybody in the world is going to be looking at it. And of course satellite trackers are going to be looking as well. So what did we see? Not much, but it didn't go without a trace. You might be quite fascinated to know that it was observed. You might be wondering, what on earth is that? We'll get into that in a second. We had some clues. The United States, as secretive as it can be about its military space program, they still care about not killing people. So they issue notice to airmen, mariners about where they're going to drop their stuff. Rockets have this nasty tendency of dropping boosters and spare parts and stuff. We don't want that dropping on boats and airplanes and people in general. So we have this international convention. These positions where we think stuff might fall out of the sky, and it would be a good idea to stay out of it. So in Zuma, they obviously had this exclusion zone right off of Cape Canaveral, where the booster was going to drop off or come back to Earth and all that kind of stuff. And then the second stage, they decided they were going to deal with it somewhere in this Indian Ocean. Okay, all well and good, but what does that mean? That gives us the first clue of what the orbit will look like. We've got two data points. We've got this, and you've got this. And from that, we were able to derive search orbits. Then, the whole, circus that became the Zuma launch happened. And a Dutch pilot flying over Sudan saw this vortex in space and posted it to one of our colleagues in the Netherlands. This Dutch pilot has actually observed this kind of stuff before. And we have a colleague, Marco Lenkenbroek, who's actually an archaeologist, kind of guy, and his hobby is satellite tracking as well. And he got this thing and knew exactly what it was. It was right here. These points here are where the aircraft and the photographs from the pilot showed So we definitely have at least the fuel, and that's what we suspect this is, from the second stage. So that confirmed the trajectory. Now, it also confirmed that our initial assumption of the orbit was too low. So we were looking too low for the wind. It was probably about 1,000 kilometers altitude. Why was it spiraling? I'm not quite sure, but we do know that some space second stages behave like this. That's the last data that I know of. But being the amateur satellite trackers we are, we started searching. In my case, I was searching 28 megahertz at a time. So we have 100 megahertz of spectrum. And one thing the United States is pretty dogged about is we eventually find their stuff on radio. And we've actually got a pretty nice map. I can tell you by what type of mission it is, where we're probably going to transmit. They may not transmit continuously, and we've got to be very determined and watch for a long time, but eventually we'll see a signal. So I started searching S-band, 28 megahertz at a time, and scanning, and going through plots. Going through plots that look like this, and searching, hitting the tap key a lot, and looking through blank spectrum, or seeing satellites you know about. And like much like our visual observation stuff, the software overlays the Doppler curves of known satellites. Like it was green line. Then I come across this thing. Green line. Wait a minute, it doesn't look like the S curve of a lower orbit satellite, which we would expect Zuma to be in. This is a Doppler curve of something higher curve. So I'm like, what on earth is that? So I thought, reduce the data. This is not Zuma. This is a subsequent image that I took after I did the analysis. This fuzziness here is a data sideband. So I'm looking at the signal and I'm like, it's talking. Not only am I seeing a carrier, but I'm seeing an upper and lower sideband, plus and minus 1.7 megahertz of the signal following the same Doppler characteristics. And by looking at the bandwidth, I'm also starting to figure out some more information about the data rate of the satellite is sending. Even though I don't have a very good signal-to-noise ratio, I'm able to determine all of this information, which all becomes characteristics of the hunt to figure out what it is. Fortunately, we've already developed Doppler curve fitting software, and I hit the identify button behind the keyboard with my little bit of data here, and boom, 26113 it says, almost instantly. I'm like, oh, that's interesting. What the heck is 26113? I've never seen it before, and I've been observing and cataloging this stuff for years now. So I went to Google, like all researchers do, and typed in NORAD 26113, and it came back as NASA image. Oh, okay, that's not very exciting. I see that kind of stuff all the time. In fact, I've got a whole catalog of space probes and higher orbit because the scientists like to put satellites like image into that orbit because they can look at the poles. They can look at the Earth from very unique angles and from far away from it as well. And they can go through the Van Allen belts and other field lines around the Earth and kind of explore and study that area of space. So it's not uncommon. There's lots of them out there. So I wasn't overwhelmed by it. But as I do, I just didn't put it in the catalog and walk away. I kept reading about it because it was just, I generally do that with every unique mission that I find. So I went to a website called, it's maintained by the European Space Agency called the EO Portal, and was reading their little report on it. And after I got through about a third of the report, I'm like, they're talking in the past tense. They didn't come out and say the thing was dead until I got near the end of the status of the mission, but they're talking about all the great things that image did and how it was one of the most successful missions that NASA had in the early 2000s and whatnot. And it just struck me as like, the thing is dead. So I did a bit more Googling, and that's when I stumbled across the failure of the mission report. And in 2005, image just switched off. It didn't report for duty one day. And it sent NASA scrambling, getting telescopes that came at it. They figured it could be a rogue, micrometeor hit, some kind of other issue with the spacecraft. And eventually, after going through a very painful process, they realized through a design error and a single event upset, the most likely cause of image failing to report for duty that day was a little circuit breaker, an electronic circuit breaker on the spacecraft was tripped, probably by some high energy particle impacting the electronics. Unfortunately, the design didn't allow them to reset the switch or the circuit breaker. So the transponder communication system had no redundancy, so the satellite was fully functional, but couldn't hear us or talk. So what they waited for was, okay, the satellite periodically passes through eclipses. And every few years, the eclipses line up and get a really long one. So they wanted to wait for the battery to go completely dead, because they knew when that happened, the thing would reboot. It's like pulling the plug in the computer and plugging it back in, it'll reboot up. Once it reboots, part of the code says, turn on the radios. So they waited and waited, and the big eclipse came and went, they didn't hear the satellite. So they packed up all the old computers and all the stuff they used for image, stuff that I don't know where, we'll get to that in a minute, and sent all these scientists and engineers on other projects. I forgot about it, stopped looking. So I studied the signal a bit more, and looking at my data, I was actually able to determine the rotation period of the spacecraft. So from that, the NEO portal was all very useful again. It told me what its nominal rotation rate was. And my figure was very close to the rotational period of the satellite. So another piece of evidence that was really pointing at this really truly being an image. Not only that no other spacecraft in orbit would have the same Doppler curve and repeated orbit after orbit after orbit. It also started displaying characteristics of the signal, the sidebands, rotation period, etc. NASA at first was reluctant to accept that it was image, but they were searching really hard. They had enough convincing data. All the scientists in the background are telling the NASA guys, it's like, no, it's image. They're like, well, we can't say that publicly because we have a copy of this telemetry we can get. And then what it turned out to be is they didn't have any hardware left that could speak the language of image. So they were in this awkward position where they're like, okay, some guy, literally that's what happened with one of the interviews with the principal investigator out, Jim Birch. He said, yeah, just some guy, he emails me and sends me this report. And I looked at it and was like, he's got a satellite. So he sends that off to the whole team, and they just go all berserk. But the NASA guys are pretty, they're steely at this one. They're all very reserved, and they're like, yes, we investigate this claim, and we'll get back to you. And I say that jokingly because Richard Burley over at NASA, him and I have actually become exchanges of emails frequently about this topic and how to deliver a report. And once you realize that he's also a PhD in engineering and he's a really smart guy, he's hanged his career on being right, being accurate. And the diligence they went through, they sent a bunch of guys, probably a bunch of guys that kind of look like a lot of them got out of the field out in the parking lot at the Goddard Space Flight Center with a dish, a spectrum analyzer, and instructions to identify the satellite. So the guys went out there and they aimed the dish, and they're all standing there with their coffee, looking at the spectrum analyzer going, yeah, that's the same signal that Mr. Tilley's copying, but they still couldn't decode it. So meanwhile, I get an email back from Richard that said, does anybody have a 3 or 2-inch tape data recorder? What they're trying to pull out is the actual software, the code, that's telemetry. Because image was unique. It was one of the first of what they call the MIDEX satellites. So it was kind of a prototype. So it didn't really, it was the first one to speak a version of the language, but it wasn't fully evolved. And because image failed, they didn't maintain any support for it. They evolved their protocols and standardized in a different direction. So they need literally to rummage under desks. They probably have tables and broken legs if they were having hardware from this project supporting it. Like you could just imagine, this is what these guys were doing for weeks until finally they decoded the telemetry thing. And Richard sent me an email confirming he was 100% sure it was it. And that's when this whole story went absolutely nuts. My life changed for a few weeks, let's say. One of the kindest gestures, maybe the second most common, actually I think this is the kindest, but the one I'm going to show you guys is the coolest from the amateur perspective. This is a mission medallion, and Jim Birch, who is the principal investigator of image, couriered this to me after the confirmation of the signal. And a man of few words, There's a really wonderful video that would be of interest to anyone here that has an interest in propagation. This man is Mr. Propagation. He's one of the principal geophysical physicists that studies the Earth's magnetic field, ionosphere, and all related phenomena. And he's been launching spacecraft in orbit since the 1960s. And carries on to this day, building missions and setting stuff up to study the stuff that makes our hobby possible. So there's a great YouTube video of him giving a speech about his career on missions and stuff that he's worked on and his philosophies of this. He's a very understated man and somebody that definitely deserves a lot more recognition in our community. So, the drama continues. So in mid-February, Image started exhibiting an anomaly. It happened to be, of course, it was on Friday afternoon. And NASA goes, lights out, 5 o'clock Friday afternoon. So I sent the data to Richard Burley, and he's like, oh, okay. And so amateurs over the weekend were monitoring Image as it did this. It started doing the funky check. Oops. Oops. We'll get there, we'll get there. So the signal started going crazy. So by Monday morning, the satellite got off the air. So I was at this point, this is where the story gets even more interesting. Now I've included in the technical loop with all the engineers trying to figure this out. Because I'm the guy collecting the data, reporting to them. So I start talking to the low-level engineers, the guys that actually are trying to figure out how to fix the connector. Why does this integrator work? How to make this talk to that. Not the senior guys who are just like, make it happen. And so I get to know a few of these guys and we're exchanging information and we start debating theories. So I came back and they said, oh, this is clearly a spacecraft orientation issue. I'm like, no. The frequency of the satellite does not change and cut off abruptly due to orientation. You see a theta, you're not going to see a large frequency shift. And then I produced data from using other classified satellites that are longer, showing them passing through eclipse, failed and operational satellites, showing what happens to power systems. When the satellite passes through eclipse, the carrier frequency always rises on US designed satellites, always. And it rises in a very peculiar way. The other characteristic, if the satellite doesn't have a battery in it, it cuts off. So my theory is that it's thermal. So, and it's still, even without the battery, so that excludes the power system doing the cause. Because it's not a battery in there, it's not a voltage on the bus, it's got to be a thermal thing. So what I proposed was it was not cooling itself properly. And as a result, the electronics is probably reaching some trip point or peak. And this just happens to be, when this cut out, it's midpoint between eclipses, seasons. So it's the time of the year where the satellite's orientation is getting maximum thermal energy. So at that point, NASA said, not much. And then I noticed in the press release, well, there's a debate about whether there's a thermal issue or an orientation problem. So then I set my alarm on my watch, and I said, wake me up on May 6th at 12:30 a.m. This Image would have just passed through eclipse and would be rising in my southern horizon for the first time since Image switched off, the second time we resumed. And lo and behold, as soon as I turned the radio on and the dish got on position, there's a signal, there's sidebands, plus or minus 1.7 millimeters. So there I am in the awkward position of emailing NASA, yeah, Image is back. And at that point, they had their stuff together. Because NASA hadn't given up. They had been working in the background. Those low-level guys actually saw it, finding all this stuff in dumpsters, doing whatever they could, and they got the ground station set up. So as soon as my report came in, the next morning, literally within hours, they were on it, and they had their first command accepted by the satellite. Now they ran into other problems, because they don't have a complete software set. They don't have an instruction manual. Believe it or not. A lot of that information was lost. Look at anybody here that's been involved in engineering projects, or even in Amtrak projects. You build something today, 10 years goes by, you find it at the bottom of your junk box. Oh, I actually have to put that back in the service. I need that. How the hell did I build that? you go looking through your log and your notebook, you've got what was important at the time, which is completely useless because everything was self-evident to you then. You forgot it. So that's what happened in NASA. So they're in the situation, but we found a bunch of new things. As the satellite was going through eclipses daily, we determined the battery's purged. That's dead. There's no capacity left. That's a very bad thing for possibly putting image back in service. The science instruments need a stable platform to operate, because it takes a number of hours to set them up and get them operational. And then if you're just going to click off in a couple hours, there's no real value in it. The other thing is they're having a really difficult time getting commands accepted by the spacecraft. It just seems to be kind of random. Even though the spacecraft's telemetry and everything else is very, very good, they think they just don't know how to talk to them. They think there's just something about the image itself that was lost in the uniqueness of the spacecraft and the software. And then it comes down to, with the dead battery, limited science potential, what do we do? So at this stage, the jury's still out of whether they're going to attempt any kind of recovery of image. My best guess would be if they could solve the communication problem, figure out some software to do that. There are guys doing it. I've seen some recent news releases and whatnot that they are still working on it, and it's largely a dedicated crew of guys at NASA doing it on their own time, trying to figure it out. That we could potentially collect science from an image during the midst of the eclipse season, maybe before the satellite gets too hot, or maybe they can solve the thermal problem. Once they regain control, maybe it's an orientation issue or whatever, and maybe we can collect it and data from each part. We don't know. But it gives a really good example. The whole image story, I think, is a great example about how techniques developed, how radio art can be used in very unique ways. And you may be wondering, how does this connect to amateur radio? Well, it connects in two ways. I'm now getting emails from people that are launching CubeSats. Anybody here follow CubeSat launches or DXNL satellites? You'll know when they first launch it, it's this big haze of CubeSats. They're not launching one or two, they're launching dozens. So the problem is, how do they figure out which CubeSat is what? The Air Force just randomly assigns things. They don't know which is what. So I'm being approached by groups saying, figure out which one's our CubeSat. So I can take the Doppler curve at 70 centimeters and go, that matches this orbital element. That's the frequency you're transmitting on. Maybe, copy some telemetry or listen to the CWI down, confirm it's the one, and say, okay, that's you in the model. And when you look at an orbital prediction program, it's literally a model. You'll see this model of CubeSats drifting around. The other really cool thing about this is there's a Chinese amateur radio machine working the moon right now. And I've been collecting Doppler data about its lunar orbit and studying that part of attending. And it's a very fascinating experiment. Imagine predicting an orbit of something orbiting something else. And all the interrelated things that go on about it. Learning about orbital mechanics and teaching yourself these things. So rather than learning from a textbook, you can learn through the screen or the earphones and whatnot. The other really interesting and where it relates to amateur radio, NASA asked me, another PR people said, what can we do for you? And I said, you can damn well QSL. As far as I know, this is the only QSL card NASA has ever sent to anyone acknowledging the reception of orbit missions. So I guess this is a unique prize. But so that was kind of, it was funny that at first when I asked them that, there were a bunch of engineers like, oh, we don't do that, this is an amateur, I'm an amateur radio operator, but this is not amateur radio. My response to that is, think of the legacy of utility stations and amateurs and shortwave listeners would send QSL cards to utility stations. And utility stations would acknowledge often because it gave them useful information about how they're being heard, the quality of their signals, and everything else from experienced radio operators. So I said that back to NASA, and they said, maybe you're onto something. And the other thing, really cool thing, if you're really into the DX side of listening to deep space, there is a small core group of guys that actually listen called Space Pros. When Cassini was around Saturn, they were listening to his TT&C beacon, all the missions around Mars, all the stuff that's floating around the asteroids out there. Pretty much anything that's in space right now is being monitored by amateurs. And We're not collecting telemetry because the signals are too weak and our antennas are too small, but we can still hear the carriers. So we can collect Doppler data, we know whether they're behaving properly or not. There's a lot of stuff you can obtain about the satellite itself, its health, its characteristics, as simply looking at the carrier and simply tracking it. And all the data that can fall out of that is quite fascinating. And we can use all the skills that we have as adventurers, looking at spectrum every day and listening to it to kind of delve those secrets out. And we can also provide, and I like to think we provide, a public service by providing the world some level of transparency about how all the nation states of the world are using space. Space doesn't belong to anybody. I kind of look at it as a world national park. And if we don't look there and verify independently what's actually going on, then I don't think we can really call ourselves free people. So unless there's any questions.
Aren't you afraid someday some guy in a black suit?
Well, actually, here's what they do. I mentioned Greg Roberts earlier. So he was at a presentation much like this. He was watching an astronomy conference. And he was giving a presentation, standing at the podium. And at the end of it, maybe there's a guy in a black suit in this room right now. I don't know. A gentleman in a suit came up to him, handed him his business card. He worked for the external affairs of the United States government. And said, you know, the U.S. people are very nice people. You know, you should find another hobby. and Greg said to him, I said, well, thank you so much for sharing that, but I think I'll pay off. So Greg sent me the gentleman's name, and I did a little bit of Googling as I do. And I found that he was a commissioned officer that was stationed over in Langley, Virginia. And who knows anything about Langley, Virginia, you know, knows what he is. So I think that's the only known encounter of any satellite observer that I know of in the Western world that has come across him. He was very polite and respectful. Yes, sir. Yes, very aware of it. I'm actually, one of the gentlemen, when I was approached by one of the launch high school kids in Southern California that are launching a satellite, Irvine 1, it's going to walk in a rocket labs mission very shortly. I posted on my Twitter feed, and one of the guys came back and said, oh, we use our software to figure this out. I said, well, no, you can't. And we've been lobbying you guys to add the ability to extract the Doppler data. You guys can't see it out. We take it away because it interferes with your ability to code telemetry. We use it to figure out all the questions that these guys are asking. So you guys are really good at collecting telemetry and data from the satellite in an automated way, but you're not learning anything about the orbit. You need to know the orbit before your stuff will work. But if you can make an automated search program that multiple users around the world can use, then we can magnify this ability from 1 or 2 people to hundreds. Yeah, that's been my suggestion to them. There should be an ability to take unidentified signals, or signals that are not known in the catalog, especially after new launches and stuff like that. Be able to identify them, pull them out of basically a herd, a flock of satellites that have just been recently launched. And then amateurs can feed back to the U.S. Air Force and say, hey guys, we're back. You know, this is it. We're not going to wait for 6 months for you guys to figure it out. We've already got it figured out. This is this, this is this, this is this, this is this. You can catalog them, do what you want. We've already figured out what A, B, C, D are. This is this satellite, this is this one. And maybe provide some public service in that capacity. And certainly it would be helpful for the satellite operators because they're not getting used to orbital elements until the Air Force sorts it out.
I read a few years ago that China actually launched another satellite to destroy another rocket.
Yes.
Is that fake news?
It's not fake news, actually. The Chinese launched an ASAT test, and they chose a very poor target. They chose a target in an 800-kilometer circular orbit, which happens to be a very popular orbital region for weather satellites and pretty much anything else in low Earth orbit. Because it's high enough to avoid the usual atmospheric drag problems, and it's low enough that they can get high resolution imagery without having to go crazy with optics. So when the Chinese did that, they destroyed a defunct weather satellite to demonstrate that we can blow things up in space. They left thousands of pieces of debris and added to that cloud, that are pieces of debris that are floating around. And if you happen to impact one of those pieces of debris head on, or they're going in different directions, or the velocities are insane. And small pieces, 1 centimeter, like a page or something, can destroy a satellite, kill someone if they happen to be spacewalking or whatnot. So it was a very poor demonstration. A few years later, there was USA 193, which was an American spy satellite that went to Earth when it was launched into orbit. The US government decided at the time to destroy it in orbit. They did it very differently though. They waited for the satellite, they claimed that it was full of hydrogen and fuel, and they didn't want it to land and harm people. I think what they didn't want to have happen was the spacecraft in an uncontrolled re-entry land like in Red Square, or something like that, and have somebody picking through the technology. So what they decided to do was send out one of the Aegis class destroyers out by Hawaii, wait for the thing to pass over just before it was going to enter, and fired a rocket and a missile at it and blew it up. That was the American response to the Chinese. It's like, yeah, we can do it too. And we've already got it deployed. And we can do it with that Navy. So there were some other earlier tests in the 1980s where they also did from F-15 fighters that have a missile that they can do as well. And that was demonstrated on the That's right. I didn't really get into the whole story of it, but the kind of conjecture afterwards was when people were standing at the podium and said, well, we can't answer that question. You'll have to talk to SpaceX. That whole thing, yeah. There's a lot of conjecture going on there. We don't know what government agency owned it. We don't know for sure whether it was really lost. It could still be in orbit for all I know. My thinking on it, the type of orbit that it would be in, would lend itself to 2 missions. It's either a radar surveillance satellite, or it was a missile defense test. That's my theory. If it failed, I would expect to launch something similar. And they did launch something similar a year before, and it was very similar orbit. It actually passed very close to the ISS, mysteriously. And we don't know why they were doing it, but it was too close to be coincidental, like within kilometers of the ISS. Yeah, well, that's the thing, right? People are looking every night. Once you get into satellite tracking, it's not like you need to be looking at a specific spot. I often will set my camera up and just leave it running all night in one position. You do that every night, and how orbits work, eventually everything in the sky will pass through. So you just keep collecting data with a number of other observers doing the same, kind of like the sat-nav said. The data will just pile up, and the guys are spewing out the results. Even if you get an unidentified, you don't know what it is, another guy's going to pick it up, another guy's going to pick it up, and then one of the analysts will put the dots together and say, it's this. So that's how it works.
Hang on. Just a second. So, Scott is, I think this, he could go on for an hour or 2 hours. Okay, so I think what we need to do is have Scott kind of do a scrub or something if you're really interested in talking to Scott about and answering questions and stuff. We need to break for lunch because we need to come back here and carry on at 1:30. So I'd like to thank Scott for your presentation. And so let's head out. There has been some draws made here, so there's 20 lucky people or so. And then Scott will be here for a little bit, so feel free to pin him down and ask him questions.
Yeah, well, that's the only one. That's the only one. Selling on eBay for $10 grand.